Before we finish up, the authors took a little bit of time to describe the use of isotopes in understanding some of the sources of water to ecosystems. And isotopes are a very important tool that we use, and so we're going to spend a little time to understand some of the basics of how we use different isotopes of hydrogen and oxygen to understand some of the dynamics of water in ecosystem. Stable isotopes are useful tools for tracing the movement of elements or compounds through ecosystems. In this course, we're going to talk about stable isotopes for water, so hydrogen and oxygen. We'll talk about how we use stable isotopes of carbon and also nitrogen. So here, let's do water. Part of the reason that people look at the isotopic composition of water is that it tells you a little bit about the source of water to ecosystems. Now, as a review, this is basic chemistry, but two isotopes of an element differ in the number of neutrons in the nucleus. Now, why that's important is that these different isotopes differ in their physical properties more strongly than their chemical properties. So the chemistry is the same. They differ in their physical properties more strongly than their chemical properties. So chemically, they react more or less the same, but physically, they're going to have slightly different properties. Now for water, we're going to focus on the ratio of deuterium to hydrogen. And hydrogen, in general, will have one proton and one electron. Deuterium will have a proton, but sometimes it also has a neutron in there, as well as one electron. So chemically, it functions the same as hydrogen, but it has this extra neutron in it, making it slightly heavier. Now, when we think about the ratio of deuterium to hydrogen, we need a standard to talk about, and that standard tends to be ocean water. So when we think about deuterium to hydrogen ratios, most of the water that you get in seawater or ocean water is going to be H2O, and there will be no deuterium in the water itself. 99.985% of water is H2O instead of, for example, DHO, where you have one atom of deuterium and one of hydrogen. Now the ratio of deuterium to hydrogen in that standard is 0.00015575. So that ratio is relatively low. And we don't necessarily talk about these ratios on an absolute basis. We usually use a standard, and that standard is going to be this number right here. So when we're going to talk about water and isotopic ratios of deuterium to hydrogen in water, we'll use this as a standard and talk about how much deviation you get from this standard, which talks about relative enrichment or depletion. Now in this case, the more deuterium you have in a sample, the more positive that sample is. I'm not going to worry about units here and how we calculate it, but we're going to give some numbers, and if you see a more positive number, that means you're going to have more deuterium in it. Now the key for thinking about how we're going to use isotopes of water, well, isotopes of hydrogen in water, is that evaporation discriminates against water with deuterium. Water with deuterium is heavier than water without deuterium, and so water without deuterium is going to evaporate a lot more readily than water with deuterium. And so the more evaporation you have, the more enriched the remaining pool of water becomes in deuterium, and the more depleted the evaporated water becomes over time. Now on the other hand, condensation raises the D to H, the deuterium to hydrogen ratios of resultant water. So when water condenses, it's deuterium that tends to condense before deuterium containing water before hydrogen containing water. Now when we see how this plays out in the real world, if we take a look at the ratios of deuterium to hydrogen in water, it tends to have a signature of about 0, because that's what our standard is. And the ocean water is going to have the same ratio as our standard. When evaporation occurs, the water that's evaporated enters the atmosphere. And because evaporation discriminates against deuterium containing water, it's going to have a negative ratio. So there's going to be less deuterium in the vapor than you expect. When that vapor condenses and rain comes out of it, that rain becomes more enriched because you're more likely to have deuterium containing water in that rain because of the condensation favoring the heavier water than the lighter water. Because you're losing some relatively enriched rain initially, the resultant vapor becomes even more depleted. And when that forms clouds and it rains out of those clouds, that water is going to be more enriched relative to the clouds, but more depleted relative to the previous rain. And then the final vapor that ends up leaving that cloud and moving on and down the line is going to be even more depleted and have less deuterium in it than vapor earlier in the process. So those are some of the basic dynamics of what happens to water with evaporation and condensation and how we can trace the movement of water through the atmosphere. But another factor that's really important is that there's a positive linear relationship between air temperature at the time of precipitation and the D to H ratio. So what that means is that if we were to draw a graph, temperature is here on the X, and then the ratio of deuterium to hydrogen in precipitation, there's a positive relationship. So by knowing the deuterium to hydrogen ratio, the isotopic ratio of water, we can infer what the temperature was when it rained. As a consequence, summer precipitation has a higher deuterium to H ratio than winter precipitation. So if I were to give you a sample of water and you were to take a look at the isotopic ratio of it, if it was relatively high, for example, that would probably be summer precipitation. Really depleted without a lot of deuterium in it, that would be winter precipitation. And the way that we use that is that we'll often take a look at groundwater, for example. When we look at groundwater, we can take a look at the isotopic ratio of the water in that groundwater and see whether it was generally came from water that was rained down during the summer or during the winter. And then when we look at plants that might be trying to access groundwater versus water from recent rains, we can start to infer whether that plant is using groundwater or shallow water. So it's an inferential approach, but by knowing the ratio of the isotopes in water and some of the basics of the physics and chemistry associated with water, for evaporation, condensation, for example, we can infer the temperature at which the precipitation occurred and also use that to separate out different sources of water that plants might access, because we're going to have different signatures in groundwater as we are for shallow soil water. Now, water is also going to have isotopic ratios of not only hydrogen and deuterium, but also of oxygen, O18 and O16. So just as we were taking a look at the D to H ratio in soils, or in water, we can also take a look at the O18 to O16 ratios in water too. And that's a perfectly fine way to do it. But in general, the patterns that we see in oxygen in O18 to O16 are pretty similar for hydrogen, for D to H ratios too. So it doesn't necessarily matter which one you look at, you get more or less the same answer.